We, on behalf of Astrophysics Group, RCAA 2021, are going to present a pedagogical video on cosmological distance ladder. Cosmological distance ladder is a series of methods of measurement of distance of astrophysical objects in order of increasing distance. It consists of number of rungs, each rung employing unique method for measuring distance. But the important point is that measurement of distance in the lower rung forms the basis of measurement in the next rung, each measurement giving the accuracy of measurement. So this is the cosmological ladder consisting of different rungs. First rung enables us to measure distance up to solar system. The second rung, which uses parallax, enables us to measure distance of nearby star, and subsequently all the other rungs will give us methods of measurement of more and more distant stars, galaxies, galaxy clusters, etc. Okay. Now, the lowest rung that involves measurement of the astrophysical objects or the planets inside the solar system. And of those measurements, first is the measurement of distance of moon, and that was done by laser ranging, where a beam of laser is allowed to reflect from moon's surface, and measuring the time it takes, one can very accurately measure the lunar distance from Earth. Then next distance measurement involves radar ranging, which is also a very accurate method for measurement of the distance of the planets inside the solar system. This gives an example of how the distance of Venus from Earth can be measured using the radar technique. Radar technique. That radar technique also gives us confirmation regarding this astronomical distance, that is the distance between the sun and Earth. And that measurement, that astronomical unit, the distance between Earth and sun, accurate measurement of distance, leads us to the next rung of our ladder, that is the stellar parallax measurement, where the distance is obtained in terms of parsec. So when we go outside the solar system, then one cannot use laser or radar technique. Instead, one have to use the stellar parallax method, where the parallax means that when we observe a distant star from Earth at different time of the year, then there is relative displacement of the star with respect to distant fixed star. When we observe this star in December, its position is obtained, apparent position is here, and in June its apparent position is here. So it is displaced, and more closer the star is, more will be the displacement and more will be the angle, this parallax angle. Okay, and one can measure this parallax angle, that from the parallax angle one can determine this distance from in the units of this and in terms of the parallax angle. And more the angle, more closer will be the star to Earth, and less this angle decreases, that means the star is further and further away from us. And if the angle subtended is 1 arc second, then distance is defined as 1%. And this is one of the most accurate geometrical method for finding out the distance of nearby star which is instead of light year, we use the distance unit parsec. Now, the measurement of the parallax angle from the surface of the Earth is sometimes not sometimes it's not easy, or there are some disadvantages of this of measuring the parallax angle from the surface of the Earth. And to find out or to measure the parallax angle of the more distant stars, physicists go to outer space, where in the outer space satellites are satellites are there. Two kinds of artificial satellites, two artificial satellites. Another is Gaia, stations stationed in space. The Hipparchus worked between 1989 to 1993, and it is capable of measuring the parallax angle up to the order of, to the accuracy of 1 millimicrosecond, and that gives us the measurement of the distant stars as far away as 1000%. And Gaia, which was launched in 2013, and which is still working, that gives us accurate parallax angle of distant stars objects up to the order of 10 microsecond, and that allows us to see the astrophysical objects as far away as 100,000%. So with the parallax method, with using parallax or measuring the parallax from space with the help of Hipparchus and Gaia, we are now able to see objects or detect objects or measure distance of the objects as far away as 100,000%. But if we have to go beyond that, beyond Milky Way, up to the galaxy clusters, then we have to we cannot rely on this parallax method. For that, we have to go some indirect method. Those indirect method include uses the standard candle method. And for discussion of other rungs in the cosmological distance ladder, over to Abhijit.
So to measure distances of distant stars, the parallax method have limitations in that in the more distant star, the parallax angles will be very small, for which we need a very high resolution instrument to resolve that. Now, to go beyond the objects which can be measured using parallax method, indirect methods are used to measure distances of cosmic objects, and in this method, the standard candles are used. The standard candle means it's an object which has a known luminosity, whose luminosity is known. And the idea behind the standard candle method is that if a standard candle is taken a distance away, its illumination or its luminosity decreases, and from the decrease in luminosity, we can measure how far the distance, how far the object is. So the standard candle is an object that has consistently the same luminosity and has an intrinsic luminosity, and owing to inverse square law, the brightness of an object falls inversely as the square of the distance. So knowing the brightness, observing the brightness and knowing the luminosity, we can find out how far it is from us. Now, in terms of magnitudes, apparent and absolute magnitude, this we get this relation, which is small m minus capital M equal to 5 log d by 10, where small m is the apparent magnitude, capital M is the absolute magnitude, and d is the distance of the object in parsec. So this magnitude distant object is used in measuring distances using standard candle. And while using this relation, the crucial point is that we need to know the absolute magnitude of the standard candle. Okay. Now, for distant stars, the spectroscopic parallax method is used, and in this, the Hertzsprung-Russell diagram is applied, and the Hertzsprung-Russell diagram is basically a plot of stars where you plot luminosity of the stars against the color index. Now, here in the Hertzsprung-Russell diagram, we find a strip which is more or less diagonal, where most of the stars are placed, and this is called main sequence. The stars, for most of their lives, they stay in the main sequence, and of this main sequence, we also have stars which are actually past their life towards the end of their life as stars. In the top portion, we have the giants and the supergiants, and in the bottom portion, we have the white dwarfs. So the stars which are in the main sequence, the main sequence is actually employed in measuring distances using spectroscopic parallax. Now here what is done is the spectrum of a star is obtained, and from the spectrum, the brightness and color of the star can be derived. Now from the color, we can get the luminosity of the star from HR diagram. Now knowing the luminosity and the brightness, we can find out the distance of the star using the magnitude distance relation. But the problem with this spectroscopic parallax method is that it involves some error. Now, why that error comes? It is because the main sequence is not a line, it is a band of stars. So corresponding to a particular value of color, we have a range of luminosities, which gives rise to the measurement of the error in the measurement of distance. Now, this error is can be reduced considerably when we use this technique in a slightly different way, and this is called the main sequence fitting, where we take, instead of a single star, we take a cluster of stars. Now what is done here is that the luminosity color index plot is obtained for the stars in that cluster. So we get a HR diagram for that cluster. Now this HR diagram is compared with the standard HR diagram, and which will be shifted from it. And from the shift, we can measure the distance of the cluster from us, because the shift will be a measure of the difference of luminosity in the luminosity distance relation. So this is an application of the spectroscopic parallax method. Now, when you go to the next run for more distant objects, another standard candle is used, which is called Cepheid variables. Now, Cepheid variables are stars which are pulsating, and they are actually have a variation in their brightness with very regular periods. Now, these periods typically ranges from 1 day to 50 days. So here we have a graph of showing two such periods, one with a longer period and the other is a shorter one. In 1910, astronomer Henrietta Leavitt showed that for the Cepheid variables, there is a linear relationship between luminosity and period. And here is the plot of luminosity and period for Cepheid variables in Milky Way, as well as in the Large Magellanic Cloud, which is a satellite galaxy of the Milky Way, and we see that they fall in a straight line. So this is the thing that is applied, or that is used in finding out distances with this method. So what is done is that we detect some CFIT variables and measure its period, and from the period we get the luminosity straight away from this graph. And once we get the luminosity, we can find out the distance using the magnitude distance relation. Now this method actually takes us to a distance of up to 100 million light years, because we can find out we can see CFIT variables in galaxies, in those galaxies where we can resolve the stars. So once we obtain, or once we detect a CFIT variable in one galaxy, we can measure its period, and from its period we can get the distance using the magnitude distance relation. So we can go up to 100 million light years using this method. The next method, or rather the next standard candle that is used, is type 1a supernova. Now supernova are exploding stars when the stars actually end their life. Now, so type 1 supernova is a particular type of supernova which occurs in binary systems in which one of the stars is a white dwarf. Now, here what happens is that the white dwarf, it accretes matter from its companion star, and as the mass of the star, the white dwarf increases and it reaches the critical mass, which is equal to 1.44 the solar mass, the Chandrasekhar limit basically, the entire star, it detonates, it explodes wholly, and in a spectacular explosion. And the light curve that is obtained for this supernova explosion is very distinct, and it is shown in the diagram in the right hand side. Now, because the critical mass is fixed, which is 1.44 the solar mass, so the type 1a supernova explosions consistently reach the peak luminosity, which is constant. So all type 1a supernova attains the same peak luminosity, and this is the fact which makes type 1a supernova a standard candle. And using this peak luminosity, once we can measure the peak luminosity, we can find out the distance using the magnitude distance relation. Now, with this method, we can go really to very high, very large distances of up to 10 gigalight years. So this is one example where we see in the slide how a distant galaxy where we cannot resolve the stars, but we can see this supernova which is there, which is clearly visible and attaining its peak luminosity in the photograph marked 0 day, and then fading away. So by measuring this peak luminosity, we can find out how distant it is. Okay, so up to this distance, we can use these standard candles. Now, beyond this, the standard candles are no longer applicable, and what we can use to measure distance is the Hubble's law. Now, we know that the universe is expanding, and due to this expansion, the galaxies are moving away from each other. So what we see from us is that the galaxies move with a speed of recession, which is proportional to the distance the galaxy is. So this is called Hubble's law. That means the velocity of recession of a galaxy is proportional to the distance it is from us. So more distant a galaxy is, more will be the velocity of recession. So the Hubble's law is given by V equal to H naught D, where H naught is a constant, Hubble's constant, which depends upon the rate of expansion of the universe. So now the velocity of a receding galaxy can be obtained by measuring its Doppler redshift. So by measuring redshift, we can directly get the velocity, and from the velocity, we can find out what is the distance, what is its distance from us. So that is how we can find out the distance of galaxies. Now, there are some disadvantages to this method. The disadvantage comes from peculiar velocity of the galaxies. Peculiar velocity means the galaxies they may be moving apart from their from the apart from due to the expansion of the universe. Due to the expansion of the universe, they are moving away from us. But apart from that motion, they can be moving around, say, a cluster of galaxy structure, or if it is a cluster of galaxies, they may be moving towards or away from each other. And these peculiar velocities are of the order of around 2,200 to 300 kilometers per second, and they add considerable error in the measurement of redshift, and hence for the distance. So the Hubble's law method is not reliable for distances less than 100 million light years. Now beyond that distance, the peculiar velocity is become less. I mean, the error that is included because of peculiar velocities are less. So the Hubble's law method is used for distances which is more than 100 million light years. Another source of error is that as we look deeper into the universe, we are actually looking backward in time. So for that, if we when we are using this relation v equal to h naught d, h naught is the Hubble's constant at the present epoch. Now, if we look at a very at a distance very far away, that means we may be looking at a different epoch where the rate of expansion of the universe may have been different. So for that, this h naught will also be different. So that actually gives rise to some error in measurement of distance. Of course, this error can be reduced if we can find out h naught for that epoch by some other means. And one such mean is that if we can detect type 1a supernova along with that. So from the observation of type 1a supernova, the value of h naught can be obtained, and hence the distance can be obtained. So that is how this method is used. Now, here in this slide, I have shown a picture of the Hubble Space Telescope, where we, in the inset, we see the a galaxy which is supposed to be the farthest galaxy that has been observed, and this galaxy has a redshift of 11.1, and which translates into a distance of 13.4 billion light years. So that is the distance up to which we can go using this method. So now, just going for the summary of distance measurements, we have in our the cosmic distance ladder, we have the rungs as the radar use of radar ranging, which is applied for solar system objects. Then the parallax method, which is obtained for nearby stars, and then the spectrographic parallax method, which are mainly applied for clusters of stars or for distant stars. Then MS fitting is also a part of it, and then we have the Cepheid variables standard candle for still further distance, and then the supernova type 1a, and finally the Hubble's law. Thank you.